All right, so today we're gonna talk about the next lecture, which is lecture 4. So before we do so, we talk about what we covered last time for a little bit. So last time we talked about two things mainly. We were wrapping up the discussion about phase, um, and then we talk about phase diagram. And then we talk about heat conduction, which is given by this particular formula here. Okay, so we talk about power, which is the rate of heat flow through some kind of, you know, well, we use an example of, like the wall of the room, and the heat flow gonna flow um, per unit second. So instead of talking about just heat flow, we talk about heat flow per unit time. So Q over A give you power, which is in watts. Okay, so watts equal to joules per second, which is divided by time. And depending on the material, you're gonna have different heat conductivity. So we have the table in the last lecture, so you can take a look. And then it depends on the area. The larger the area, the better heat flow. And it depends on the difference in the temperature between one side and the other side. So this one is kind of, if you're confused, you can think about when you are in the room, you are turning on the air conditioner. It's especially nowadays extremely hot, right? Every day. If the outside temperature is really high, then in the room it's gonna be a little bit warmer than usual because heat flow gonna be higher because delta T is higher, and then it depends on L, which is the thickness of the wall. All right, so the thicker it is, then the more distance heat has to travel, so it's reduce the heat flow rate. Okay, so that's one um, thing we talk about, and then we talk about like a new kind of like larger topics which we're gonna continue also for today, which is thermodynamical process. And the first thing that we need to understand is what we call the first law of thermodynamics, which is given by this equation. Okay, so we have three things, three variables here, which is related to any thermodynamical process. It doesn't matter whether you are talking about the process that involve gas, like ideal gas, or you can talk about the process that involve other things like liquid or something like that. Even though in this course we're not going to talk too much about the process that involve liquid because that's a little bit harder to describe. But what we have here is very universal. It can apply to essentially any process that involve heat exchange of um, any object. Okay, so we have three variables: delta U, which is the change in the internal energy. So for ideal gas, which is gonna be mainly what we talk about in this um, lecture, U is given by this simple formula 3 half n, the number of molecules, times Kb and times T, the temperature, right? And then one important fact that we emphasize many times is that, oh, actually I should write delta T here also because it's delta U, so it's delta T. So delta U depends only on the change in the temperature, okay? It doesn't matter like how you move from one point on the PV diagram to another point. We're gonna see an example in a few minutes how we can use this fact, okay? But if you know the end point and the starting point, you know the change in the temperature, then delta U is all, all done, right? You don't need any more than that, which is different from the remaining two variable, which is work. This is equal to, well, in terms of, calculus language, I'm gonna write it this way. So it's gonna be integral of P dV which might look scary to some of you, but actually it doesn't mean anything other than the area under curve of the PV diagram. Okay, so this just means this. Okay, the integral of P dV, well, V we use as the variable for the integration, and P is usually the function that depends on V, the volume, so you integrate, and then you get the area under curve in the PV diagram. That's gonna give you W. Okay, and the important thing for W is that there's a sign difference between positive and negative work. For our convention, positive work, I'm running out of space here, so I'm gonna write it here. So positive work means V expand. That's probably the only thing you need to remember, because if work is negative, then it's the other way around. Okay, so if volume expands, then work gonna be positive. That's probably the thing that I will ask you to just remember, because it's gonna be a lot easier if you get this right from the beginning. And that's for W. And then Q, usually it's a little bit harder to calculate Q directly. So you're gonna use the first law here to calculate Q. Once you know what is delta U, once you know what is W. So rearranging the first law of thermodynamics, then Q is usually given by delta U plus W. Okay, so that's kind of like how the flow of the calculation gonna look like usually. And to demonstrate like how we use this kind of concept in the actual calculation, so we have this example here, which we're gonna try to solve. All right, so any thermodynamical process gonna involve the PV diagram. So essentially, thermodynamical process just a fancy word of how you move on the PV diagram. Okay, so in this case, it's a very simple process. It's just a straight line going from here to here. Okay, that's one kind of process. You can have different processes. Like you can move from A to B, like this way. That's also a valid process. That will give you different work, different heat transfer, or you can have something like this. So you have infinitely many ways, many possible ways to move from A to B. Okay, but in this particular one, it's just a straight line going horizontally. That means during this process, pressure does not change. Right? It should be clear from the diagram that it's a horizontal line, so it's a line of constant P, the pressure. So it's gonna be what we assume here. All right, so let's see what can we do in terms of calculation. So let's read the question together. So we have the figure shows a PV diagram. Okay, that's fine. And an ideal gas, which is good. So there's a lot of formula that we can use for ideal gas. And the absolute temperature at B is 1/4 of the absolute temperature at A. Okay, so that's very important piece of information. So this point and this point, I can write temperature at point B to be TB, temperature at point A to be TA. Okay, and they are not the same. Okay, not only that, it's given that TB is 1/4 of TA. Okay, so whatever the temperature here is, okay, which you can calculate because you know the pressure here, which is 1.5 atm, and you know the volume here, which is 0.5 liter, right? So you can use PV equal to NKBT or PV equal to nRT to calculate the temperature in principle. But the thing is that we don't know how much gas we have. We don't know like how many molecules, how many moles, right? So we don't have enough information here. But what we have here is enough to calculate what's the volume at point B, VB here. And that's essentially what is being asked in the first question, first sub-question. So how do we do that? Well, this is the information that we have here. So remember, excuse me. So remember the formula, which is PV equal to nRT, right? And then we also did something like this, which is PV over T equal to nR, which is a constant because there's no gas leaking in or out. So that means PV equal to PV over T is constant for this gas. What does it mean? Well, it means that if I take P at point A, V at point A divided by T at point A, it's going to be equal to P at point B, V at point B, and then divide by T at point B. And the pressure at A and B is the same, right? Because going from B to A is just a horizontal straight line in the PV diagram. So we can cancel out PA and PB right away, right? We don't need that kind of numerical number in the calculation here. So in the end, we just have VA over TA equal to VB over TB. And then we also know the relationship between TA and TB, right? So from this, I can rewrite TA equal to 4 times TB, right? So I can just substitute here TA into this equation. So I have VA over TA, which is now 4TB, equal to VB over TB. And by doing so, I can cancel out TB also, like this. Okay. So in the end, what I have is TB is 1/4 of, not TB, VB is 1/4 of VA, right? And that's essentially the answer for the first question. Well, at least it's enough for us to calculate what VB is. Because VA is 0.5, right? So a quarter of 0.5 is just 0.125 liter. So that's how we get the answer for the first one. Okay, by comparing PV over T of gas at point A and point B. Okay, so this is part A, so let me write that down. So that's done. Okay, now for B, how many joules of work done by or on the gas in this process? What is done by or on the gas? Well, you might be wondering like what's going on here. So essentially, it's just asking what is the sign of W. That's all it's asking, because once we know the sign, then we can answer that right away. So for part B, let me change the color. So for part B, the work done again is the integral of P dV, which is the area under the curve. And the area under the curve for this one is very easy to calculate because it's just a rectangle. Okay, so it's just the base times the height. And the height is 1.5 ATM. You need to change this to Pascal, so you need to multiply by roughly 10 to the 5 Pascal. So this is our pressure. And then times the base, which is 0.5 minus 0.125 liter here, right? So if you do this, then you're gonna get the answer to be, well, let me just calculate it. So 0.5 minus, so 1.5 times 10 to the 5 times 0.375. So you get 56250 joules. So that's the work done. But this is wrong. So quick question, what's the symbol between P and V? Where? Sorry. At the integration? What? Oh, it's D, sorry. Here, right? Okay. So, yeah, it's kind of like integral of f dx or something like that. But in this case, we are integrating for V as the, like variable. So it's P dv. Okay. All right. So we have this number for work, which is the area under the curve here. But this is wrong. Why is it wrong? Because if you get this, it means that your work is positive, which is not true because positive work means the volume is expanding. But in this case, the volume is not expanding. In this case, volume is shrinking because you start with 0.5 and then you go down to 0.15. So volume decreases. So that means you have negative work. So it should be negative here. So, okay, it's fine, but can I just stick in a negative sign here, even though I know it has to be negative because the volume decreased? Well, what I did wrong also is this part here. Okay, I used volume VA and then minus VB here. But actually I should have written VB minus VA because it should be the final volume minus the initial volume. Okay, so it should be the other way around. So that's why I messed up the sign here. So here I should have written 0.125 minus 0.5 here. Okay, this is the correct expression. So it just gives you that, reverse of the sign, but it's kind of showing you like how I got the sign from. Okay, but I mean you can either just calculate the way you feel like, and then you put the minus sign in the end, and then you say it's minus because the volume decrease. That's also okay, right? As long as you have like a valid reason to put in a minus sign, that's totally okay with me. All right, so we have a minus sign which is indicate that the volume shrinks. So volume shrinks means you're compressing the gas. Compressing the gas means you are doing work on the gas. Okay, that's it's just the language that we use. Right? Because you are compressing the gas, then you are pushing in the gas. You are giving in some energy in form of work here. All right. So for B, that's done. Now for the next one, did the internal energy of the gas increase or decrease from A to B? Well, internal energy, so essentially it's asking what is delta U here. Well, delta U is again depends on just the temperature, so it's just 3/2 N, we don't know big N, that's fine, KB and then delta T, right? So what is delta T? Is T at the final point, which is TB, minus the initial point, which is TA. Okay, and it's given in the question already that TB is less than TA, right? By like TB is just a quarter of TA. So when you do TB minus TA, it's pretty sure that this number gonna be less than 0. it's a negative number. So the internal energy of the gas decrease, right? In other words, the temperature of the gas is also going to be lower once you reach uh, point B. Okay, once you reach point B. And then the last one, did heat enter or leave the gas from A to B? Well, the last one is where you apply the first law of thermodynamics. So let's write that down. So we want Q, right? So heat, enter or leave, essentially asking you what is the value of Q. So Q in this case is delta U plus W. We don't need to use an exact numerical value for delta U. It's not asked here, but you can calculate that if you want. But here you just look at the sign of each variable. So W is negative. Delta U is also negative. When you add two negative numbers together, there's no way you can get positive. So in this case, Q also is less than 0. So Q less than 0 means the gas lose Q, so heat leave the gas. Okay, so that's what it means by negative Q here. So if you get Q to be positive, then that means heat enter the gas. Okay, so that's how usually the problem solving strategy is going to be for this kind of problem. Is kind of like you need to work step by step, like for the information given in the problem, and then in the end you're trying to find Q. Usually that's what's happening here. Okay, so hopefully this is not too bad for everyone. So today we're gonna talk about a few possible ways to move around the PV diagram. So that means we're gonna talk about a few thermodynamical processes. So if you don't have any question, then I will start talking about that. Oh, yes? Uh-huh. How do I get less than 0 here? Because delta U is this in front, which is always positive. That's nothing gonna change. So it depends on the change in the temperature, right? So essentially, asking the sign of delta U is the same thing as asking whether the gas gonna be colder or hotter once you reach the final point. But it's already given in the question that TB is a quarter of TA, so we know right away that it's gonna be colder at point B. So if it's colder, then delta U gonna be negative because it's less temperature. Okay, no problem. All right, so that's a very good point because usually delta U can be calculated right away because most of the time you're gonna know the change in the temperature. All right, so let's talk about a few ways to move around the PV diagram. We're gonna talk about 4 particular processes, but again, there are infinitely many of them. But these four are the easiest to calculate, okay? And they have like specific name that might or might not be, intuitive to all of you. So let's see. All right, so we're gonna have different processes. The first one we're gonna talk about is called the isochoric process, which is just a fancy name of saying that it's the process where V is constant. Okay, so what does it mean? It means that it's the process where the gas does not expand or does not shrink. So volume is constant. And if you plot in the PV diagram, it's gonna be the case where you move along the vertical line, because that's how you keep the volume constant, right? For example, you move from here to here, point A to point B, down, right? So volume does not change. So the only thing that changed, well, not the only thing that changed, because temperature will also change. But it's clear from the diagram that the pressure changed from PA to PB, like this. Okay, so the temperature will also change, because you can use PV equal to nRT to, calculate the temperature at point A and B. But since volume does not change, that means the area under the curve is 0. Okay, because there's no area here. So that means for this particular process, W is 0. When W is 0, then it's very easy to write down the first law, which is used to be delta U equal to Q minus W, right? But W is 0 in this particular process, so we can ignore them, ignore the work done. So that means, well, okay, let me keep this. So that just means delta U equal to Q. So what does it mean? It means that all the heat that you put into the gas will be used to increase the internal energy with 100%, because you don't waste any energy for work, where work is 0, right? So everything you put in terms of heat will become the change in the internal energy. Okay, so let's write a little bit more about this. So we know that delta U is 3/2 NKBT, NKB delta T, right? Delta U depends only on the temperature. So that's going to be equal to Q. Okay, or I don't have to use this formula. I can also use 3/2 equal to small n R delta T equal to Q, right? This is the same thing as the ideal gas having to form PV equal to nRT or equal to N big N KBT, right? It's just the difference of whether you want to describe your gas using the number of moles or the number of molecules. That's it, okay? So in this case, I also can do the same here. In particular, especially when you write it this way, right? This should kind of remind you of the equation that we talked about last week, which is Q equal to C times delta T, right? And then remember what is C? C is called heat capacity. So try not to get confused with the other formula, which is MC delta T. This C should be big C, which is heat capacity. Heat capacity is the mass of the object times small c, which is called specific heat. Okay, different thing, small c and big C, right? But m times small c gives you big C, which is called the heat capacity, which is essentially just all the number multiplying in front of delta T here. Okay, so now if you compare these two equations, they look kind of the same. Okay, so for the gas, if we change Q to be on the left hand side, so we can write N to be the number of moles times 3/2 R, and then times delta T, right? So it's kind of the same as actually the lower formula here, where Q is the amount of heat flowing into the gas or flow out from the gas, depends on how much gas you have, the number of moles, times some constant, times the change in the temperature, right? So sometimes we're gonna write this in this way, N times C sub V times delta T, right? And then we're gonna call this CV here to be molar specific heat, right? So it's the, actually it's just heat capacity per 1 mole. Okay, so molar heat, molar specific heat. And the thing which will be confusing to some of you is that molar specific heat depends on the kind of process. So that's why we need to do a subscript V here, because it's the molar specific heat for a constant V process. Next, we're going to talk about a process which is constant in P, the pressure. You're going to have also Cp, which is the molar specific heat for constant pressure. And that's going to be different. Okay, so this is the point which is quite important for you to distinguish between different processes, right? So I want to make it clear at this point that the molar specific heat in this equation gonna depends on what kind of process. But essentially what this all means is that if you know that the process is isochoric, which is fixed in the volume, right? If you know the change in the temperature, you know right away how much heat you need either to put in or to take out. And you use this formula here. Okay. So if everything is confusing to you, you can also just ignore this CV thing and then just remember, or take a look at this formula instead, which is equivalent to what we have down there. Okay. So this is probably the most, like the easiest process that we can think of, because it's very simple. We can do a little bit differently by talking about the next process, which is called isobaric. Now, if you have any word that contain this kind of bar, usually it depends, it's related to pressure. Like some of you might know that the device that we use to measure pressure is called barometer. Okay, so the one that gives you weather forecast every day, like high pressure, low pressure, we use barometer to measure that. So ISO means constant, right? Doesn't change, the same. So in this case, isobaric, well, you can guess that it probably just means the process in which constant P, so P is constant. So P does not change during the process. So if we draw the PV diagram, well, definitely it's gonna look different from above here, isochoric, because now pressure need to change, and it need to change in the way that, pressure is constant, so volume need to change, and volume change the way that pressure is a constant. So it's gonna be the horizontal line like this. So you can go to the right. Well, the example that we did in the earlier page is from right to the left. It's also isobaric because constant P. Okay, so we have the change in the volume. And P is fixed, but volume change. So we can go from VA to VB like this. And then this is P, this is V. Okay, so now it's clear that work is not zero. because you have the area under the curve, which is a rectangle here. So now, if we want to use delta U equal to Q minus W again, let's do it one at a time. So let's talk about W here. Okay. So W is just the area under the curve. So it's essentially just P times VB minus VA. Okay. Exactly the same as what we did in the earlier page. All right. But we can do a little bit more because we can use the ideal gas law, PV equal to nRT, to substitute into this equation, because in the end what we want is we want to have the work done in terms of the change in the temperature. Okay, you'll see why later on, but that's not that's what we want. So by doing so, I can just substitute, right? PVB becomes nRTB, right? So this becomes nRTB, and then VA and P pair together also give me another term of nRTA. Okay, so nR is the common factor, so I can write TB minus TA, which is essentially just the change in the temperature. Okay, so TB is the temperature at this point, TA is the temperature at this point, right? So the work done is the area under the curve, right? And also equal to nR times delta T, right, for this particular process. So the reason why we want to write W in terms of the change in the temperature, because delta U is also written in terms of the change in the temperature, right, which is the usual formula. So delta U, there's only one formula, no matter what process you use. So delta U is just 3/2 small n R delta T, right? So always this formula, no matter what process. So Q, using this equation, is delta U plus W, right? So now you see like the motivation of rewriting W in terms of the change in the temperature, because now I can add them together. So delta U is 3/2 nR delta T plus W, which is nR delta T. And together I have 5/2 nR delta T. So using the same kind of, nomenclature above, is n in front, 5/2 R times delta T. So this one I can write it in terms of Cp delta T. Right. So it's the same as what we had earlier, because we want to write this in terms of, molar specific heat. Well, above is for constant V, but now we have constant P. So we can see that the value is different. Cp is 5/2 instead of 3/2. So again, this is molar specific heat for constant P, so that's why we put in a subscript P here. So let me talk a little bit about this molar specific heat kind of thing. So molar specific heat means that, let's say you know how many moles you have. Let's say just one mole, right? If you have 1 mole of gas and you want to increase the temperature of the gas, right? So how much heat you need to put in? If you talk about isochoric, which is constant volume, all the heat goes into internal energy because there's no work done. So you don't waste any energy in terms of the work done. Okay, so the heat required is given by this formula. 3/2 R times N times delta T. But if you want to increase the same gas, same amount of gas by the same temperature, but now you do it via isobaric process, which is this one, right? So in this case, you have to spend more energy to do that. You have to put in more energy to increase by the same amount of temperature. Why? Because not only that you need to spend some energy in increasing the internal energy, but you also need to spend some energy in expanding the gas. That requires energy also. Okay, so the work done is not zero here. So the energy that you put in had to be split into increasing U and also non-zero W, the work. Okay, so that's why the specific heat here is larger than the one above because of this reason. Okay, so Cp is not equal to Cv. All right, any question at this point? All right, so if you don't have any question, then let's talk about the next one. Well, we have volume constant, we have pressure constant. So next one, naturally, we probably gonna talk about constant temperature. Right? And constant temperature is something which is called isothermal. So as the name suggesting, iso mean not change, right? Same, like the name isotopes. Some of you might know this from chemistry. Isotope is the same chemical element with different mass number, right? So it's called isotopes because chemically they behave the same thing, but just difference in the neutron, the number of neutrons. Okay, so isothermal is constant T, no change in the temperature. If there's no change in the temperature, you should think already about the change in the internal energy. Delta U equal to 3/2 nR delta T. So if T is constant, delta T is 0. So in this case, delta U is 0 also. Okay, so isothermal process is the process where internal energy does not change because temperature is not changing. Okay, constant T. When we draw PV diagram, it's not going to be a straight line any longer. So let's figure out what kind of curve we have here. So P and V here, right? So we want to move along this around this PV diagram. So PV equal to nRT again, right? So I think by the end of this course, we're going to write PV equal to nRT probably more than 20 times. So just bear with me there. So nRT here, and T is constant, R is constant, N is constant. So on the right hand side, everything is constant. So we have a curve where P times V is the constant. So this should remind you of some kind of curve where you have y times x equal to constant, something like that. It's called a hyperbola. Okay. So a constant temperature curve is a hyperbola on the PV diagram. For example, if you are here at this point, you want to expand the volume, but you want to keep the temperature to be constant. You have to move along a particular curve, which is a hyperbola, and reach the destination. Okay, you have to follow this one. You cannot just go straight like this. That's not a hyperbola. That will not keep the temperature to be constant. Okay, so it has to be a hyperbola from the first point to the second point like this. Okay, so V1 and V2. So for a given temperature, that corresponds to one hyperbola on the PV diagram. Because this section of the curve here is one section of a hyperbola which extends infinitely from very high P to very low P. And this is for one particular temperature. If you have different temperature, you're gonna have a different curve, which is also a hyperbola, but it's a hyperbola where the right hand side is different number. Okay, so you have this kind of, curve which is all hyperbola, but hyperbola with different constant. These sometimes are called isotherms, which is essentially the hyperbola of different temperature on the PV diagram. Okay, so every isotherm is a hyperbola, but depending on the temperature, then it's gonna be different isotherms. Okay, so if you move along isotherms, your temperature does not change. Now, because it's no longer a straight line, to calculate the work done requires a little bit more work than before. So the work done is the area under the curve here. Now we need to really do the integration. And some of you might be glad because this is where the calculus class that you have taken is really useful. Okay, so let's calculate the work done, which is the area under the curve, shaded by the blue color here. So W is integral of P dV from V equal to V1 to V equal to V2. Okay, so it's just a standard way of writing area under the curve by integration. Now the thing is that we must know P as a function of V, otherwise you cannot calculate it, right? But we know from this equation that PV equal to nRT, which is all constant, right? So P is just this constant nRT, all constant, divided by V. So from that, I can put it to this equation here, right? And then I can write integral of V from V equal to V1 to V equal to V2 of P, right? But P now is nRT divided by V dV. But nRT is a constant. Anytime you have a constant, you can take it in front of the integral sign, which is very convenient to do. And then you just have this 1 over V times dV. Okay, and integral of 1 over V dV, well, you might remember from your calculus, integral of 1 over x dx, that gives you a natural log function, ln, okay, natural log of V, right? But we need to put in the limit of integration at the next step. So I'm not going to do that at this step. So we're going to write it this way. But that's what we need to do. Okay. So those of you who don't remember exactly what is ln is just log of the natural base. So base of e. E is 2.7128, something like that. So with the integral, with the limit of integral putting in, you have log of V2 minus log of V1, right? And then if you have the difference in the log, you can combine it and write it as the log of the ratio between V2 and V1. That's going to be the work done in this process. Okay, so it involves the logarithm of the ratio of the volume. And you can check that the sign still makes sense, because if you have V2 larger than V1, right, so let's write it this way. If we have V2 larger than V1, then log of V2 over V1 will be larger than 0. Okay, you can try this in your calculator. It's going to be the case. But if you have V2 less than V1, then it's going to be log of something less than 1. That's going to be less than 0. Okay, log of negative number is undefined, right? But we are not going to encounter that because the volume is always positive. Okay, so this is very different from what we had earlier. So let me go back here. So in the isobaric case, the area under the curve is the difference in the volume. Okay, so that's where the negative sign comes from when you go from large volume to smaller volume. Okay, but here, because it's the log, then you need to take the log of the ratio between V2 and V1. And the log is the one that gives you whether it's positive or negative, right? So don't get confused and write log of delta V or something like this. That's not going to work. Okay, so be careful about using this formula for the work here. So the work done is given by this formula for isothermal process. Right. So in this particular case, we go from small v1 to larger v2, so work done going to be positive. For negative work, you need to compress the gas. So it just means you go from v2 back up to v1 like that. Okay, so the direction of the arrow just directly give you the the sign of the work done here. Okay, so we have written down the work done, which is this formula, and delta U is 0 because there's no change in the temperature. So that means Q, which is delta U plus W, but W is 0 for this process. So Q is just W, which is given by the same formula here. Right, so this is the process where Q and W share the same formula. So there's no change in the temperature. So what does it mean? It means that all the heat that you put into the system will not be spent in increasing the internal energy at all. So all the heat that being put in will get spent in terms of work. Right, so you put in 100 joules, the gas will also do 100 joules of work expansion. And if you take out 100 joules of work, it's going to be from shrinking the volume, right? So there's no change in the internal energy in this case. All right? Now before we talk about the last process, which is called adiabatic, maybe it's a good time to take a quick break. So again, I will set a timer for 10 minutes and we will come back after the timer runs out. All right, and meanwhile, you can just shoot me any question if you have. Okay, so let's take a 10-minute break and then we come back later.